I'm going to be talking about 3 of my favorite things: JavaScript, Unicode, and 90s gangster rap. So if you're into one of those things, you've come to the right place. So hi, I work for Opera Software in developer relations, and both as part of my job and in my spare time, I like to collaborate on open source projects. And one example of such a project is Unicode.js, which I wrote a couple of years ago. And nowadays, it's part of Node.js itself. It ships with Node, so if you want to play around with it, you can just require it and start using it. You don't have to npm install anything. Now, the Unicode algorithm is what browsers and other software that deals with URLs use to convert internationalized domain names like these into their pure ASCII form so that they can still be used at the DNS level. Now, I wanted to write a JavaScript implementation of that, and I always thought that it would be really simple because the algorithm is well defined in an RFC. So I figured I would just port that algorithm into JavaScript, and that would be it. But while I was working on this actual implementation, I ran into lots of new things that I didn't know about JavaScript. And that's what this talk will be about, basically. But first, does anyone know who this guy is? Yeah, of course. Everyone knows it's Jay-Z. It's a famous American rapper. But a little known fact about him is that he decided to write a JavaScript program once. And instead, he ended up writing a song about his frustrations with the language. And you may have heard it before. It's called 99 Problems. Now, don't get me wrong. I love JavaScript, even though I'm making fun of it here. But just like with any other programming language, if you don't know the entire language by heart, and really, who does, then you're going to be surprised every now and then. That's just what life as a programmer is like. And that's also why we have websites like phpwhatthefuck.org, which neatly lists all these weird quirks in the PHP language. And similarly, whatthefuckjs.com, which does the same thing for JavaScript. And of course, everything on these websites can perfectly be explained if you just look at the specification, or for PHP, the documentation or the implementation. But even then, if a particular behavior of the language is confusing to a lot of people, then that is a bit of a problem. So I think the way JavaScript handles Unicode is, well, very surprising to say the least. But before we get into that, let's talk about Unicode itself, just to make sure we're all on the same page. I'm going to tell you the absolute minimum about Unicode that you need to know in order to work with strings in JavaScript correctly, and nothing else. So it's easiest to think of Unicode as sort of like a database that maps any symbol you can think of to a unique number called the code point, and to a unique canonical name for that symbol. So that way, it's really easy to refer to any specific symbol just by using the unique name or that code point. You don't have to use the symbol itself to talk about the symbol. So for example, Unicode maps the Latin capital letter A to the code point U plus 0041. And this is a hexadecimal number. And usually, code points are formatted like this, in hex, with the U plus prefix and 0 padded up to at least 4 digits. Now, another example is the letter small, Latin small letter A, which is a different letter altogether, so it gets its own code point and its own canonical name. You get the idea. So there's a lot of stuff in Unicode. Each symbol simply gets its own code point. And there's a lot of weird stuff as well, like there's a snowman symbol in Unicode, and I'm not sure why you would ever need it, but it's there if you want to use it. And then there's everyone's favorite character, the pile of poo. That's the actual canonical name for the symbol. So as you can see, the code point is 1F4A9, which consists of 5 hexadecimal digits. So you may be wondering at this point, how many code points are there, or what's the highest possible code point value in Unicode? Well, the possible code point values range from 0 to 10FFFF, and that's a little over 1.1 million possible symbols. So to keep things a bit organized, Unicode divides this range of code points into 17 planes that consist of about 65,000 code points each. And the first of these planes is called the BMP, and it's probably the most important one because it contains all the most commonly used symbols. So most of the time, you don't need any symbols or any code points outside of the BMP to write a text document in English or Spanish or even in German with all your crazy characters. So just like any other plane, it contains about 65,000 symbols. Now, there's a group name for all the other planes combined as well, and they're called the supplementary planes. So this totals up to about 1 million other code points. So this is the vast majority of the Unicode code point space. So these are called astral planes or supplementary planes. And we also talk about astral code points or astral symbols. It just means it's a code point that lies within one of these planes. Now, astral code points are very easy to recognize because whenever you need more than 4 hexadecimal digits to represent that code point, it means it's an Astral code point. OK, so now that we have a basic understanding of Unicode, let's see how it applies to JavaScript strings. You may have seen stuff like this before in string literals. It starts with a backslash followed by x, followed by 2 hexadecimal digits. And now that you know about Unicode, it's easy to see what these digits refer to. They refer to a Unicode code point. So this is, in fact, another way to represent the string ABC in all caps. And this is another way to represent the string ABC in lowercase. And this is useful because sometimes you have these weird characters that are maybe hard to type on your keyboard, or you want to avoid encoding issues if you save the file with a different encoding for some reason. And then you can use these escape sequences to represent such characters. So this is useful, but we're still limited to only 2 hexadecimal digits here. So this can only be used for code points up to FF, which is not a lot of code points. Luckily, there's this other type of escape sequence called the Unicode escape sequence. It starts with a backslash followed by U, followed by 4 hexadecimal digits. So this is much better. We can make the same escapes as before, but we can also escape characters for which we need 4 hexadecimal digits, like 2661, which is the code point for the white heart symbol. So this makes it possible to escape all these code points, all those in the BMP, actually. But what about all the other planes? What about those Astral code points? We need more than 4 hexadecimal digits for those, so how do we escape them? Or another way to phrase the question, what about the pile of poo and other equally important Astral symbols, of course? Now, the answer is we can actually escape those, but it's kind of sort of complicated. In ECMAScript 6, it will, in fact, be really easy because you have these things called Unicode code point escapes. They start with a backslash followed by U, followed by braces. And between those braces, you can use up to 6 hexadecimal digits, which is enough to represent any Unicode code point. Now, by using this type of escape sequence, you can simply escape any Unicode symbol based on its code point. It couldn't be easier. But if you need something that works today in ES5, the unfortunate solution is to use this thing called surrogate pairs. So in this case, each escape represents the code point of a surrogate half. And it's only when these 2 surrogate halves are combined together, they form a single Astral symbol. And this is annoying for a number of reasons. For starters, the surrogate code points that are being used, they don't really look anything like the original code point. Now, there are formulas that you can use to calculate these surrogates based on a given Astral code point and the other way around. And here's a JavaScript implementation of those formulas. You don't have to learn this by heart, but apparently you have to know that this sort of thing exists if you want to deal with strings in JavaScript. Now, anyway, this whole concept of using a single escape to represent BMP symbols and then using 2 separate escapes for Astral symbols is a bit confusing, and it has a lot of annoying consequences throughout the entire language. So for example, let's say you want to count the number of symbols in a given string. My first thought would probably be to use the string length property, right? And in these examples, indeed, the length property happens to reflect the number of characters in the string. And that can be explained because if we escape the characters in the string and we count the number of escape sequences, well, we see that there's only 1 escape sequence in each of these strings. So that kind of makes sense. However, let's try some other similar-looking characters. This is the mathematical bold capital letter A and the mathematical bold capital letter B. They're different symbols, so they have completely different code points. And in this case, they're Astral code points. And because of that, they have a length of 2 in JavaScript rather than 1, even though there's only a single symbol there. So what JavaScript does is it kind of exposes these surrogate halves as if they were separate characters. And this is really confusing because we as human beings, we generally think in terms of Unicode characters or even graphemes. So similarly, a string containing only the pile of poo character has a length of 2 in JavaScript. And there's a very obvious joke to be made here. But instead, I'm going to show you a real-world example of where this actually can break things. So this is Twitter a while ago. It allows 140 characters per tweet, as you probably know. And their backend doesn't mind what kind of symbol you're using. So Astral symbols, BMP symbols, they all just count as 1. Now, at some point, they had a bug in their front end, and their JavaScript counters simply read out the string length without accounting for surrogate pairs. So because of this, the counter would decrease in steps of 2 for each Astral symbol you would enter. Because of this bug, it wasn't possible to tweet more than 70 piles of poo at a time. It was absolutely terrible. Now, another example is countable.js, a JavaScript library that counts how many characters and words and paragraphs you enter in a text area, for example, and then it displays those numbers elsewhere on the page. So the first thing I did when I saw this demo page was to enter a pile of poo, and it counted it as 2 characters instead of 1. So these are just some examples, and really this is an honest mistake to make because the behavior is so surprising. But really, if you're writing a JavaScript library or you're doing anything that involves strings whatsoever in JavaScript, you kind of have to make it work with all symbols, not just those in the BMP, because sooner or later, one of your users is going to enter one of those emoji or other Astral symbols. And the easiest way to verify that you're doing the right thing is just to do what I did and test it with some Astral symbols. So basically, just throw some piles of poo in there and see what happens. So this is what it felt like to enter that pile of poo. I just kind of knew that something would likely go wrong, you know? So yeah, that's not good. Anyway, getting back to our question, how can it be done? How can we accurately count the number of symbols in a JavaScript string or the number of code points in a string? Well, one thing you could do is use a third-party library like Unicode.js, for example. It has utility methods that can help you convert between strings and Unicode code points. So the UCS2 decode method takes a string and returns an array of code points, one for each code point in the string. So if you then get the resulting, the length of the resulting array rather than getting the length of the string directly, this gives you a more accurate result. And no matter what you're doing, you kind of have to account for surrogate halves in JavaScript when you're dealing with strings like that. You don't have a choice, you have to do this. Now, in ECMAScript 6, there's a similar solution to this. You could use array.from, pass in the string, and that would return an array of strings, one for each symbol in the original string. Internally, this would use the ES6 string iterator, which is also new, and the iterator deals with whole code points whenever possible, so you won't ever have to deal with these surrogates yourself anymore. This is not the most efficient solution to this problem. You could also use a regular expression if you just need to count the number of characters to replace those Astral characters with ASCII symbols, for example, but we'll get to that later. Now, I've made a tool that takes any string as input and then shows the escape sequences for any special characters within the string. So it's kind of like a hex dump, except that the output is valid JavaScript, which is sometimes more useful. Now, with this tool, it's really easy to tell which Unicode characters the string contains exactly, even if the symbols are non-printable or just white space. Now, depending on your use case, it's not that simple. We know how to count code points correctly, but if we're being really pedantic, then counting the number of symbols in a string is even more complicated. In this case, JavaScript is telling us that these strings are different, but visually there's no way to tell. So what's going on here? So I took these two strings and I copied them into the tool that I just showed you, and this is what I got. The first string uses the code point f1 for the n character with the tilde on top of it. And then the second string uses a separate n character followed by 0303, the code point for the combining tilde. So combining marks in Unicode, they just get applied to the previous symbol. That's how they work. But we don't really care about that. If we want to count the number of symbols in these strings, we expect an answer of 6 in both cases. So how can we make that happen? Well, the answer is we can use Unicode normalization, which is another new feature in ES6. And this already ships today in Chrome and Opera. So if you want to use it in other browsers, you should of course include a polyfill. It's called unorm, and it's available there at the bottom. So basically, before you account for these Astral symbols and surrogates, you just call normalize on that string. You pass in the normalization form that you would like to use, and this effectively gets rid of these lookalike symbols. Now, is this solution perfect? Well, it kind of depends. If you need to support stuff like this, in which case I count 9 different symbols, you know, this is basically a string with lots of combining marks that get applied to the previous character. That's why it looks so weird. So I count 9 symbols here, but even our most pedantic function still counts 116 different characters. And you can see why. So if you need to support situations like this, it's probably best to use a regular expression that removes all these combining marks and grapheme extenders from the string, and then gets the length just like we did before. We'll get to that later. Another example is reversing a string in JavaScript. It seems very simple, and in fact, if you Google for it, you'll probably end up with a solution that looks like this. You just take the string, split it into an array, reverse that array, and then put it back together into a string. And indeed, this seems to reverse the string ABC correctly. Now let's try another one. Let's try mañana. So here we're reversing the string mañana, where the n with the tilde is represented by a single Unicode symbol. And again, the reverse function seems to work as expected. But if we try the other mañana, where the N and the tilde are two separate characters, now we see that the tilde gets applied to the letter A rather than to the N symbol, which is probably not what you would expect. And also, if we try it on an astral symbol, like the pile of poo, well, we now know that these consist of two characters in JavaScript, two surrogate halves. And now the reversed result is completely unusable because the surrogate halves are in the wrong order, and this is a form of data loss. So even something as seemingly simple as reversing a string becomes really tricky if you need full Unicode support in JavaScript. Luckily for us, a brilliant computer scientist named Missy Elliott came up with a bulletproof algorithm that accounts for these issues. The algorithm goes, I put my thing down, flip it, and reverse it. And indeed, by swapping the position of any combining marks with the symbol that they belong to, as well as reversing any surrogate pairs before further processing the string, all these issues are avoided successfully. So thank you, Missy. Here's a JavaScript implementation of that. I packaged it up into a library called srever. So if you ever need to reverse a string in JavaScript, feel free to use it. Now, these were just some examples, and this behavior really affects other string methods too. It's everywhere. So for example, string.fromCharacter code allows you to create a string based on a Unicode code point. But it only works for code points in the BMP range. If you use it with an astral code point, you will get an unexpected result. The solution here is to calculate the code points for the surrogate halves yourself and pass them as separate arguments. And this is really unfortunate because it means you have to implement those formulas that I showed you earlier. Of course, you could use a third-party library, but again, this is introducing a dependency just to create a string out of a number, which really shouldn't happen. Luckily, in ES6, there is a solution for this in the form of a new method called string.fromCodePoint. So it's kind of similar to string.fromCharacter code, except that this actually works properly, including for astral symbols. Similarly, the character add method on the string prototype is also affected by this behavior. If you use character add to retrieve the first symbol in the string containing the pile of poo character, you'll only get the first surrogate half instead of the whole symbol, which may not be what you expect. There is no solution for this in ES6, but there is a proposal to add something like string.prototype.add to the language, which would do the same thing as character add, but it would deal with full symbols instead of surrogate halves whenever possible. The character code add method has a similar problem. If you use character code add to retrieve the first code point of the first symbol in the string, you'll get the code point of the first surrogate half rather than the whole pile of poo character. Now, in ES6, there's a new method called string.prototype.codePointAdd, which is kind of like character code add, but it deals with full symbols instead of surrogate halves whenever possible. And the links at the bottom, they point to polyfills that you can start using today, and this works in every browser that way. Now, another example is, let's say you want to loop over every symbol in a string and do something with each separate symbol. In ECMAScript 5, you'd have to write a lot of boilerplate code just to account for surrogate pairs, because you want to consider them as a single character. Now, in ES6, this will be much, much easier, because you can just use for-off. This will use the new string iterator, which I talked about before, and this will deal with whole symbols instead of surrogate pairs automatically. Now, this behavior affects pretty much all string methods, so be really careful when you're using them. And this is really unfortunate, but you know, as Tupac would say, that's just the way it is. Some things will never change. Now, another similar problem lies with regular expressions which operate on strings. So for example, the dot operator in regular expressions only matches a single character. But because JavaScript exposes surrogate halves as separate characters, it won't ever match an astral symbol. So I would expect the result of true here, but it's actually false. So let's think about this for a second. What regular expression could we use to match any Unicode symbol? Any ideas? Well, we can't use the dot operator, as we've demonstrated, and also that wouldn't match line breaks. We can fix the line break problem by using something like this, which would match any character, but still it wouldn't match astral symbols, because as far as JavaScript is concerned, those consist of 2 characters. So, any ideas? Well, what would the regular expression look like to match any Unicode code point? Well, like this, apparently. Yeah. So the first part of this regular expression matches any BMP symbol that does not start a surrogate pair, and then the second half matches a surrogate pair, in other words, an astral symbol. Now, of course, this is not the type of regular expression you would enjoy writing by hand, let alone maintaining it. So I used the JavaScript library to generate these for me. It's called Regenerate, and it works kind of like this. So here I create a new instance, I add the range of all Unicode code points to it, and then I call toString, which returns a string that can be used as part of a regular expression literal. It returns a string because it's supposed to be used as part of a build script. Here's another example that's maybe a bit more advanced. So we start with all Unicode code points, then we remove a range of symbols based on their string values, then we remove a single symbol, in this case the pile of poo, and then we call toString on that to turn that set into a regular expression. And apparently that looks like this. So once again, this is not a regular expression you would enjoy writing by hand or that you want to maintain. Imagine having to add just one code point to that set and rewriting the whole thing. It would probably take a very long time. So instead, it's much easier to just change those 5 lines of code right above the regular expression, store that in a build script, and then just run the build script again after you've modified it. Here's another example. Let's say you need a regular expression that matches all Greek symbols in the Unicode standard. So there are NPM modules that contain the Unicode data for each category, script, and block or property. So if you combine these with Regenerate, it's really easy to build complex Unicode-aware regular expressions. So here, I'm just requiring all the Greek symbols in Unicode 6.3.0 as an array, and then I'm passing that array to Regenerate, and then I'm turning that into a regular expression, which looks like this, apparently. So you may have noticed I'm using the data for Unicode 6.3.0 here, but a couple of weeks ago, Unicode 7 was released, so this is in fact out of date. So to update that regular expression, all I need to do now is just change a single line of code in the script, like this. So changing that regular expression manually would have taken a very long time, but now all I have to do was change the Unicode version number, run the script again, and just like that, an up-to-date regular expression comes out. Now, getting back to the dot operator, well, ES6 introduces a new flag for regular expressions, the U flag, and it stands for Unicode, of course, and it makes the dot operator match whole code points instead of surrogate halves. So it kind of makes regular expressions work the way you would think they would work. Here's another example. In character classes, it's possible to use ranges, as I'm sure you know. So you probably expect A-C to match A, B, and C, right? Because that's the order these code points are in the Unicode standard. So similarly, you might expect this regular expression to match the pile of poo, the flexed biceps, and the dizzy symbol, right? I mean, that just makes sense, because that's the order of the code points. But in fact, it doesn't work that way. Actually, if you run this code, it will throw an error on the very first line. It will say, the regular expression is invalid, the range is out of order. So what's going on there? Well, as far as JavaScript is concerned, this is what that regular expression looks like. So it's not trying to create a range between those two emoji, it's trying to create a range between one surrogate and then the other surrogate for the other character, which is not the right range in the first place, and because the range is in the wrong order, it throws an error. So in ES6, this is really easy to fix. You can just add the U flag to your regular expression, and that magically makes it work the way you would expect. However, if you need something that works today in ES5, you're stuck with using a tool like Regenerate to build your regular expressions for you. But nowadays, there's a better solution, and I actually just released this. It's called regex, and it's a transpiler for ECMAScript 6 regular expressions that use the U flag. So it will look through your code for such regular expressions and rewrite them completely so that they're equivalent, but so that they still work in ES5. And here's a demo of that. This is live transpilation in the browser, but of course you can use it in Node. I've also submitted a patch to Traceur, which is now implemented, so this is actually available in Traceur right now. You can start using this today. Write your regular expressions the ES6 way, and compile it down to code that works today without worrying about it. So in summary, I think it's fair to say that JavaScript has a Unicode problem, but rather than complaining about it like JC did, we should probably be doing this instead. Yeah, we should just deal with it and work around these issues, because it's honestly not that hard. And all you have to do is add some piles of poo to your unit tests. Now, there's a lot of very talented JavaScript developers here, because it's JSConf. Now, if every one of us would just submit a quick pull request that adds a pile of poo to the unit test for any library that you're using, or maybe that you've written, I think we can collectively discover lots of bugs and help get them fixed. Because I think the problem is not that developers don't want to fix these issues. I think the problem is they just don't know about it because it's such surprising behavior. Thank you.